Hello. Good morning, Cade. Good morning, Chef. Welcome. Good morning, Hamma. Welcome. Can't open that. Can open that though. There we go. Thank you, Internet Explorer. Data and data. I say data. We are not the same. Good morning, Giovanni. Welcome. CS202 student, welcome. Good to see you guys. Are we playing Fibbage? Is that the thing? I don't know what. I think I've played that game before. Oh yeah, Jackbox is a lot. That's a really fun game, actually. I really enjoy that game. Yeah, I'm gonna fix this. This is gonna bug me. Yeah, I would be able to stream Jackbox. Yeah, that might be kind of fun. That's also a dangerous game to play, though. If I ever do that, I put the stream in your hands. Okay, so welcome everyone. I hope you can hear me okay. I assume you can see me. Connection's looking good. It is 11:30, so we're gonna get started with class today. I'll be willing to accept some dynamic array questions right now if you'd like. There's one thing I do want to talk about because I've had a few questions. And it doesn't necessarily require a PDF edit, but it would be worth noting. So let's just talk real quick about the bracket operator and the at function. Now they do the exact same thing, except you see one here is constant and the other one is not, and that the at is returning a copy of the element that's in the array. And the bracket operator is returning the actual reference to the item that's in the array. Okay? So that means that it's a read-only version to access the array, and the ampersand one here, the bracket operator, that's a read and write operator or function that can be used with our array. Now, I suggest that you should check the index of these operators and functions. I suggest that you should check to see if this unsigned integer is within bounds. So this unsigned integer, it cannot be negative. So there's really no point to check to see if it's less than 0. But you should check to see to make sure that it is less than the current length of the array. That is, whatever's being indexed actually exists. Now, I suggest if it's not, you can do two things. One is you can just return a default type object, right? You can just return a default type object. Or you can call this function I've mentioned, which is exit1. So I'll just kind of show you. We will be working in this C++ window here today anyway, so might as well get it started. So there is a function in the program called exit1, or just exit. And you can pass in some integer here. And what is that? That is the return code, the exit code. So you'll notice down here in main, we return 0, and 0 means success. All right. Whatever number we return here, whether it's 322, 1, 9, something like that, this is what tells the operating system how the program did. And that's how code grade determines if your program exited successfully. Your program code grade will check to see if your program returns 0 here. And if it does, that means that your program exited successfully. Now up here in this function foo, if you call exit1, it's basically like saying main returns 1. Or the whole program exits. With error code 1. So I suggest you can do that as well. Now it turns out in one case you're probably going to want to call exit1, and in the other case it won't matter too much. If you look here at the at function, notice that it's not a return by reference, meaning it's returning a copy of some object. So if you call the default constructor inside of that function and just return whatever that object is, everything will be fine because you're returning a copy of that object you created inside of the function. But this is a little more complicated because this operator returns a reference to an object. All right, this returns a reference to an object. So I want to see if you guys understand this. Let's say I have an int foo. And then I say something, let's say, you know what? I want this to be a return by reference. And let's say I have int x here equals 4. And then I return x. Is this okay? Obviously, VS Code thinks it's fine, but is it okay? What do you guys think? Is there a problem here or no? And Chef, I will get to your question. I just want to finish this up. I do see it there. What do you guys think? Is this fine? Or is it not? And can you tell me why? I mean, I'll accept a yes/no answer if you want. I don't mind. But I do want you to think about this one. We have silence. We don't. Oh, is my thing? Let me see here. So Uchu, you're kind of along the right track here. I wouldn't say it returns the address of X, but it is returning the actual reference to X. So in some sense it does, but it is returning an int. Cade says, I think it should be okay. Well, let's talk about this. Look where X is declared. It's inside foo. So can you tell me what line number X lives until? What is the scope of X? How long does it survive? Or where does its life end? On line 7, right? So past this point, X no longer lives. Livers. And so let's say somewhere down here, I say int y is equal to foo. Or even this. This is even better. This might not make much sense to you, but I could say this. I'm returning a reference to some integer here, so I could assign something to it. You've probably never seen that before, and that's fine. If you would prefer, I could say something like int pointer y is equal to the address of foo. And then I could say y dereferenced is equal to 6. That might make a little more sense to you. Regardless, you guys are correct. X is no longer alive at this point. So when I call foo here, X gets deallocated. Or, yeah, in some sense, X no longer is alive. It gets deallocated. So what am I referencing here? And Male, when you say 4 equals 6, please do not be careful with that. 4 on there's never a 4 on the left side. It's like a bucket. It's like a bucket that contains 4, and you're gonna just kind of put 6 in it instead. You take the 4 out and you put 6 in it. Chef says null pointer. Now, I would say that's the closest answer. But the point to understand here is we're returning a reference to a variable that was declared inside of the function. You're welcome. So this is declared here. So X only lives as long as the function is called. Once the function is done being called, X is deallocated, but we just returned a reference to that integer. We just return a reference to that integer. So do you see the issue here? This is no longer alive, therefore the reference is not good. This might give you a dangling pointer. It might be a null pointer. You might segfault here. I don't even know if the code will compile. We could try for fun. But do we understand this? Do we understand the issue here? Do you see what I'm trying to say? I think we're okay. Yeah. What did I save this as? I guess I saved it as power, huh? I wonder if it'll compile. Let's see how smart the compiler really is. I hope it's not. Aha! Well, look. Reference to local variable X. So look at that. It gives you a warning, and then we could try to run it. What do you know? So I would say, Chef, you're right. Chef, you're 100% correct. Chef, you guys will see what the islands are for. But okay, so are we clear here? X is a local variable, and when we say local variable, we're saying, hey, this only lives in this locality. It only lives in that scope. So if we return a reference to it, it's not going to work. So when we come to this part here, on this bracket operator, yes or no, do you think it's appropriate to return a call to a default constructor here? Specifically in the operator, do you think it's appropriate to return a call to the default constructor? The answer is no. It's not okay because you'll be returning an address to a local variable. And your code will generate that same warning when you compile it. So it would be better to call exit1. Do you have any questions about that? In this @1, you can do either. You can do default or you can do exit1. In the bracket operator, you should only call exit1. That is, if it's out of bounds. Now, Chef had asked, does the specialized constructor go out of bounds if the size we pass is larger than the size of the type? Let me try to answer that. If you think about it, this is a constructor, so the type array has not been initialized yet. It has not been initialized yet. And so, in that sense, what you should do is you should allocate memory for that array first. You should allocate memory for this array first. The parameters that are passed in, this array is guaranteed to have the same size that the size parameter is as well. Hamma says, is exit1 the same as return1 or no? It is the same, but only from int main. Does that make sense? Exit1 is like returning 1 from main itself. It's not like returning 1 from some function foo. It's returning 1 from main. So Chef says, because don't we have to allocate a larger array than the one we pass it for the pushback functions? So I'm trying to understand here. This is going to be like a, I don't know, it really just looks kind of like this. You're going to have something like int x5 equals 3, 4, 5, I don't know, 6, 7. And then you're going to say something like my dynamic array, which holds integers. My array is going to then take in this x, which is a pointer, by the way. This is a pointer. Don't be confused here. And then you'll pass in 5 as the size. Now, in here, you're not supposed to say array equals param. That's a shallow copy. You are required to make a deep copy. So you have to say array equals new type size. So Chef, it depends on if you're doing time efficient or memory efficient. If you're doing memory efficient, the array you allocate will be the exact same size as the parameter array. If you're doing time efficient, your array should be allocated with a size that is greater than or equal to the parameter size. So in time efficient, you can do either the size. This would be memory or time. I really don't mind either. But if you say array equals new type, I don't know, size plus 100, that could be specifically for time efficient. And then down here, you make a deep copy of that parameter. Did we get there? Does that answer your question? It is a constructor, so you can initialize it with however much memory you'd like, as long as it's not greater than, I don't know, 10,000. Maybe it will be, but... Or are we still confused? All right, well, let me know on that. Or you can come to office hours. What is this thing about it having a larger array? If it's memory efficient, it won't have a larger array than the original. I don't think it says that. This constructor should make a deep copy of the parameter array. The size is passed in so you know how large the parameter array is. If you're making a memory efficient dynamic array, the sizes will be the same. If you're doing a time efficient dynamic array, you'll want to initialize the size of the dynamic array to be maybe a little bit larger. But in this case, some of them will be empty. Would you mind coming to office hours? Because I think there's a little bit of confusion here. I think, yeah. So we'll talk about it then. And if you are on the same wavelength here as Chef, you can come to office hours too, and we can do like a whiteboard, an Excel sheet, a Microsoft Paint. So if you want to, come to office hours at 2. Or maybe we can even try 12:45 p.m. if you have class, and we'll see if we can work that out. Now that we've moved past that, let's get back into recursion. So we're just going to do a brief review of what we talked about last time. All right, at least the important stuff. Remember, we're going to have a midterm on Tuesday. Tomorrow, I will post a review. I might even get to it today, but we'll see. Tomorrow I'll post a review. And it's about these things, okay? I'm not going to ask you a specific question about inheritance, but I will ask you about virtuals, which is something that includes inheritance. So you should know stuff from the first midterm, but the second midterm is not directed towards any kind of first midterm content. All right, obviously assignment 7 has been posted and many of you have begun working on it. Now, onto the recursive stuff, at least the important things. Anything that's recursive is a function that is defined in terms of itself. In C++ terms, it means the function calls itself. All right? Now remember, anything that can be done with a loop can be done with recursion. Anything that can be done with recursion can be done with a loop, though it's not always so easy. As I said somewhere down here, there is not a super easy, cut and dry way to convert a loop to recursion. You can't just kind of put this there and put this here. It doesn't always work like that. Today, with the islands, I will show you, you see these island files, I will show you a problem that is very hard to solve with a loop. But with recursion, it's much easier. So you'll kind of understand why we use recursion, and in some cases where we wouldn't use a loop. Like, why would we choose to use a loop over recursion? And that's because many problems are hard to solve with loops. So recall that recursion is memory intensive, right? I almost broke Bobby last class. I called Fibonacci the 100th Fibonacci number. And Bobby was working on it, but it did not come back very fast, right? So recursion is very memory intensive. It's like you're calling a function over and over and over again, and that takes a lot of memory. Obviously, loops use less memory. I talked about that. Remember that sometimes you can't use a loop. I mean, you can, but it would take you a while. How long would it take for the 100th number to be returned? It depends on your CPU and your RAM. In CS 302, you'll talk about something related to time analysis. Time complexity, that is. You'll hear people will talk about what's the time complexity of something like this, where you say something like O of n. I think it's big O of n. You may hear of things that are O of n log n. And usually these are pretty good. This means for n elements, you have n CPU operations. That's what O of n means. For n elements, you have n CPU operations. Now, I would say the Fibonacci number, based on what I saw there, it generates a tree, right? generates a tree, and that tree has a certain height. There's a lot of CPU operations there. I would say it might take, for the 100th number, I bet it would finish in the day. For the 1000th number, a little over a week probably. For the 10,000th number, probably a month. It gets kind of wild. Probably even longer. But I'll leave that for the CS302 instructor to teach you. So now that we've got over all of that, just remember there's three things that a valid and working recursive function has. Okay? A function called to itself. Now that's just the basic definition of something recursive. You can make bad recursive functions. Just like you can build infinite loops, you can build a function that infinitely calls itself. Sometimes I've seen you guys call the equals operator inside of your equals operator. And that's an infinite recursion on the equals operator. And then you won't be able to tell what your program is doing. So remember, you can make bad recursive functions. But if we're talking about ones that are working and valid, it has a function called to itself. It has a base case, something to stop the recursion. You might think of this as something that goes inside of the while loop condition. Right? That might say while I is less than 10. The base case is a little bit like that. But it's not, like I said, it's not a one-to-one conversion. Right? The base case is usually where you check to see if you're at the smallest kind of building block of your problem. And we'll talk about that today. If you think back to the Fibonacci sequence, if you remember, the base case is specifically talking about when n is equal to 1 or 0. That's our base case. And in the base case, we'll choose not to return a call to itself, but rather just a flat number. And the last thing we need is a reduction operation. The reduction operation takes the function one step closer to the base case. So all good and working recursive functions have these three things. Now we have one more bit of notes, and then we're spending the rest of the time coding today. All right, so I just want to include this one note. The number of times a function calls itself at most, all right, at most, describes the type of tree that is generated. So does anyone know the name of this tree? Now, you'll talk about this in later classes. It's very interesting. But you're kind of approaching, like I said, the theoretical part of this class. Do you know what kind of tree we would call this? A binary tree, indeed. That's exactly right. Why is it binary? That's because it has 2. 1, 2. So each node, this is what you would call a node, calls itself twice. That ends up being a binary tree, BI being 2. You can have unary trees. I'll build one of those today. You can have trinary. And then at some point, we'll just call them n-ary, meaning a 4-ary tree, a 5-ary tree. We don't want to get hung up on grammar here, whatever the word actually is. We'll just call them n-ary trees. So we'll say, if the function can call itself n times, it will generate what we call an n-ary, I guess it's an a-n-ary tree. If the function can call itself n times, it will generate a n-ary tree. So I hope that makes sense. So we're going to start with a very simple function, at least 2 of them. And I may just kind of do this one in front of you to begin with, but then we're going to move on to this island one, which you're going to have fun with. You might call that a Mr. P term, but that's largely referenced in the literature. Unfortunately, I'd love to call that a Mr. P term, but I want you to try to tell me what a 17 array tree is in English. Right? Good luck with that. We're dead. We died. Look at that face. Yeah, we're dead, guys. We hit an F here. We hit an F. Yep. We had an F. 1157. 1157. No. A 17 tree is just a 17 tree. Right? If you think about it, you've got a triangle, right? That's 3. And then you've got a quad. God, what's it called? A quadrangle, right? That's 4. And then you've got a pent. I mean, if you want to talk shapes, pentagon, hexagon, heptagon, octagon, decagon is 10, right? What's 17? You tell me. It's not up to me. So what we're going to do now is first we're going to do a power function. Okay? So we're going to represent some n to the p, some integer number n to the p, which could be called as power, where we have the number n to the power p. Okay? We're going to have the number n to the power p. Now, we're going to, before we build this function recursively, we're going to do positive integer power function. Positive integer power function. All right, we're not getting in any fractions here. I'm not interested in that. We're trying to keep things simple. All right. Heptadecagon. That's a good one. That actually sounds like it might be right. So, we need to identify some things before we get started here, all right? So first, let's try to identify a base case for this. This is probably the most important part. So can we break this down? Can we break down this power into a bunch of smaller problems? And if so, what does that look like, do you guys think? Think about what power is, right? Let me kind of give you some ideas here. Taking a number to a power, if you take 2 to the third, that comes out as 2 times 2 times 2, right? So Chef is way ahead. Yes, Chef, you're 100% correct. Those are the base cases. Chef has the base case. That's correct. But let's talk about the smallest, kind of the smallest building block of this problem. When we look at it like this, it's like, it's a little bit bigger. There's some things that are involved here. But the smallest operation, the smallest problem is just a single 2 by 2, a 2 times 2. Do you agree with that? And in fact, if you wanted to be even pickier, I'll show you. Remember that any number to the 0 is 1. So if you think about it, this is 2 times, I would say 1 times 2 times 1 times 2 times 1 times 2 times 1. So do you see that this is how we're going to break this problem down? All right, this is how we're going to break this problem down. Yeah, so Chef says it would be a for loop constrained by P that is just n times n. Yes, so that's the loop, right? That's the way to do it with a loop. You want to do this with a loop? It might be something like int I equals 1 for int I equals 0. I is less than the power I plus plus. You might take I times equals n. Let's see if that works. So that's the loop. Let's take a guess here. Let's say 2 to the power 3. We're going to take 1 times 2 times 2 times 2. I would say that's correct. Yeah. So that's the loop. We're going to do this recursively now. Now, these are the building blocks. So this is kind of going to be our base case, all right? So please tell me, I guess I don't need to get rid of that. So the first thing I always like to type in my recursive functions are the base case. All right, that's my favorite thing to do. So we're going to check to see if our power, what do you say? If our power equals 0. And if our power is equal to 0, then we will return 1, right? Because anything to the 0, n to the 0 equals 1. Do you agree with that? Now, can you help me identify, or if you wanted to be even pickier, right, you could say if the power equals 1, you can return n. All right? You can go either way here, because n to the 1 is equal to n. So let's just pick 1, okay? Let's just pick 1. Let's just pick 1. So our base case will be n to the 0 equals 1, right? Now, can you take a guess at what our reduction operation is? What is our reduction operation? What are we going to do here? Remember, the reduction operation takes us one step closer to the base case. So what kind of operation do you think we'll be working with here? As I spill water on myself. I've got a big mouth, but an even bigger water bottle. What is our reduction operation? So let's specifically think about it in terms of what we check on the base case. What are we checking for on the base case? In that P here. So there has to be some reduction operation on P. And I would say Cade is, Cade's getting a little bit ahead here. I just want to identify the operation that reduces something. And so Cade is right, but I would say more specifically the reduction operation is going to be a P minus 1. Yeah, Top Wolf, that's right, a P minus 1. And if you want to think about it like this, look at this. 2 to the 5th is equal to 2 to the 0, well, 2 to the 1 times 2 to the 4th, which is equal to 2 to the 1 times 2 to the 1 times 2 to the 3rd. So do you see here that we're kind of breaking out the base cases here? And you'll see that this was P minus 1, P minus 1. We want to do another P minus 1 times 2 to the 2nd. P minus 1 here. Is it making sense? So specifically the operation, the reduction operation is this part on the P minus 1. Now we can get into the recursive part, right? Which is kind of what you guys want to jump to, and that's fine. What's the recursive part? Well, that's going to be a call to itself. Does anyone know what that might look like? I'll take the whole thing. I see Cade here has one part, so I'll put it in there. We're going to have, say, power to, what's it take here? Well, n and P minus 1. But what else? Are we done here? So the reduction operation's in here. But what else do we have to do? There's a little bit more work we'll have to do, because I think this will just come out as 1. What is happening here? So eventually this will return 1. Let's go ahead and build out our tree, why not? And I'm going to change it up on you guys, okay? I am going to change it up on you. Let's see. P equals 1. I don't know. I'm not going to do that. You want to multiply things. Yes, indeed you want to multiply them. Cade's going for the Fibonacci here. Yeah, true. You could do that. I would say, let's see here. I'd probably just say n times that. I would probably just say n times that. Or if you wanted to be picky, you could say power n to the 1. You could say power n to the 1, which will ultimately return whatever n is, right? That's going to be 2. So you could kind of take a step up here and just say, I'm going to return n times power of that. So we've got our base case. All right. We've got our reduction operation. And then we also have a recursive call. Now you're going to have to do some work here. We might call this the work. And the work is what's going to ultimately give us our result. So let's go ahead and test this out. What do you say? And while we're at it, can anyone tell me what kind of tree this generates? What kind of tree does this generate? Chef says if p equals 0, it shouldn't return n though, right? Oh yeah, you're right. Thank you, Chef. I confused myself. Yeah, if p equals 0, let's return 1. My bad, folks. My bad. So let's take 2 to the 3rd. Let's try a few of them. Let's take 3 to the 3. Let's take 3 to the 2nd. Let's take 10 to the 10. So let me remind you here. Let's see. Unsigned int. What are you mad at? Using namespace. Yeah, I don't think you should be angry at me. Though I may be missing something, that's fine. Chef says unary. Let's kind of remind ourselves here. The number of times a function calls itself at most describes the type of tree that's generated. So if the function can call itself n times, it will generate an n-ary tree. So how many times does this function call itself at most? Just 1. Oh, thanks. Thank you. Go away, red line. Thanks. It looks like just once here. Do you see that, Uchu? Do you see? It's only going to call itself once here. So we call this a one-ary tree, or if you're fancy, a unary tree. Does that make sense, folks? I would hope so. So hopefully it's correct. 2 to the 3rd is 8. 3 to the 3 is 27. 3 to the 2 is 9. And then 10 to the 10. Now that's incorrect. And does anyone know why that came out incorrect? Does anyone know why that came out incorrect? I'll show you, Synthos. I'll show you guys. Someone, while I'm doing this, can someone tell me why that was incorrect? Can someone tell me why that was incorrect? So, Chef, why was it so much faster? It's unary tree, specifically. I'll show you why. Male, you're right. No, male is the closest. It ran out of bits. The number that was generated is bigger than what can be represented in 4 bytes. All right, the number that was generated is bigger than what can be represented in 4 bytes. So you might say long here. That's a long. I think that's 8 or 16 bytes. And now we can try it again. And it should come out as something that's correct, hopefully. That's better, right? So it ran out of, it kind of did run out of memory in that, I guess they might call that an overflow. All right, you can't shove this number into 4 bytes. It has to be in a bigger size. So you ask, why is the tree unary? Well, all you have to do is build it, right? So we're going to start with this value here. Let's take 2 to the 3. And so what does that generate? Well, it ends up calling itself, right? Calls itself a few times. This will be 2 to the 2. This will be 2 to the 1. And this will be 2 to the 0. All right. And they call themselves, right? I'll make a little bit of a green thing here. So that calls that one calls that one calls that one. All right. And so what is this one? This comes out as 2 to the 2, right? And it's represented as 2 times 2 to the 2. This is 2 to the 1. And this is 2 to the 0. And then you can kind of copy these in here, right? So what kind of happens here is first, when we call 2 to the 3, it's got a little thing here. It goes, I'm going to go down 2 times 2 to the 2, which is actually 2 times 2 times 2 to the 1, which is actually 2 times 2 times 2 times 2 to the 0. And then here's where it starts to return. So then it starts to return its way back up, and it starts to do the work. Here it says, I don't know what we'll do here. 2 times 1 is 2, times 2 is 4, times 2 is 8. I'll return 8. And then we finally end up with an 8 up top. Synthos, no, this is definitely not how CMath does power. This would be extremely inefficient. So Synthos, I ask, I think, do you see that this is a unary tree? Let's look at the binary tree here. Fib calls itself twice. It says fib n-1 plus fib n-2. So it calls itself once here, and it calls itself once over here. Generating two function calls to itself from one node, representing in a binary, right? In binary, that's kind of two calls to itself. What does this one do? Well, it only calls itself once, right? Here's the only call that this will ever make to itself, if any. It says power here. There's no fib here. You can look at the other one. Let's look at the other one. See, this one calls itself twice. Here's the first call. Here's the second call. So it calls itself at most twice. This one calls itself at most once. So please, I would love a yes, no on that. Do you see, from anybody, do you see that this is a unary tree? This is a unary tree. All right, thank you. Now, Chef asked why it's faster. Well, Chef, if you think about this, for the number of p, you just call that many functions. So in this case, if I've got p numbers, say p is some value, right? P is some value. P is some value. Right? And so for whatever p is, power calls itself p times. All right? Now, what about the Fibonacci? What about the Fibonacci? Well, for whatever number it is, right? If you think about it, for whatever number, what we're working with n in this case, I'll put it somewhere else. I'll put it somewhere else. So for whatever value n is, fib calls itself twice. Or in some sense, n times 2. Times 2 times 2. So for whatever value n is, it's kind of like a It's going to be 2 to the n is what it is. For whatever value n is, fib calls itself 2 to the n. And how can you tell that? Well, look here at this tree. It'll be kind of hard to see, so pay attention, please. Up here, this is, what is this? This is 2 to the 0. You're going to have to do tree analysis later, okay? But this is 2 to the 0. 2 to the 0 is 1. This will be 2 to the 1, which is 2. And then if this happened to call itself, you get 2. Let's just go to Google, folks. Why am I wasting the time here? Let's just go to Google and let me show you. This is how binary trees work. This is how any n-ary tree works. All right, binary tree. Show me a good image here. Show me a beautiful image of a binary tree. All right, that's a good one. That's a good one. Now let's see if I can open it in Internet Explorer. Thanks. All right. Okay, look at this. Look at how many times it ends up calling itself. So what is this? This is probably Fibonacci of, this is 4, this is 3, this is 2, this is 1, this is 0. So this might be just Fibonacci of 4. So for Fibonacci 4, how many times does the function call itself? Well, it's 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus 2 to the 3, plus 2 to the 4. So actually, more specifically, this comes out to be n times, well, it's a summation. Summation from 1 to n, 2 to the n. All right, I don't have a whiteboard here. So when I ask you to generate the 10th Fibonacci number, this is summation from 0 to n, 0 to 10, 2 to the n. So 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4. Do you see how that number can get really big? And do you understand why, if you say call the 1000th number, this is a sum from 0 to 1000 on 2 to, say, n, where n, say, equals 0. This is the sum from n equals 0 to 1000, 2 to the n. What's that number come out to be? Very large. Very, very large. Very large. So, like I said, this is a CS302 topic, but are you willing to accept what I said there? I guess specifically, Chef, your question earlier. Why is power so much faster than fib? Well, fib calls itself a lot more times than the other one. So now we're going to get into the fun recursive function, all right? We're going to get into the fun recursive function here. It is acceptable. Yeah, it's not for this class, okay? I assure you. Time analysis is not for this class. This is CS202. Your job is to understand how to do recursion. Your job is not to understand why it runs slow or fast. But I gave you the hint. And it's based off of the size of the tree that it generates. Okay? So now we're going to move on to the fun one. So if you have any questions about why this power function works, let me know. Otherwise, we're going to do this one. All right, we're going to get into the islands. Are you ready for the islands? So what does this text file mean? Well, I'll show you. I kind of wrote this program already, all right? So I'm just going to briefly explain to you how it works, and then you're going to help me write a recursive function to solve some problems. So what this says is this is a 4x4 island, back to the two-dimensional arrays. Are you excited? So this is a 4x4 island. And so we can kind of break it out here. like this, where the dots are water and the X's are land. So this island is completely surrounded by water. Do you see that? This island is completely surrounded by water. I can kind of highlight it there. And then the island itself is in the middle. Let's look at some other islands. This is just how the program reads it in, so I gotta put it back to that. But let's look at this one. This is a 6x8. So we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Maybe I did this wrong. Maybe I did. Let me try one more. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That looks a little better, yeah. There we go. So this is a 6x8 island where the height is 6 and the width is 8. And we've got an island in here, right? So there's some land here. There's some land. And you'll notice that some of them are touching. You'll see that this land is touching this land. This land here is touching this land, touching this land. Am I making any sense? Obviously, this is not a real pretty island. But you can kind of see here. You can kind of see it, right? That's my only question to you. Let's look at this one. This is an 8x9. That's 5, 6, 7, 8, 9. 1, 2, 3, 4. Yeah. So these are our islands. This is kind of an interesting island. Pangea, right? That's an island. And then here's island number 4. Now look at this one. This one's very interesting. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. This one's very interesting, I hope. And that there will be multiple islands in here. Okay. So this one has 2 islands. Notice they're not touching. There's some water in between them. There's some water here. So there's 2 islands here. There's 2 islands. All right, so now that you understand what these are, we're going to write some recursive functions. You're more than welcome to write a loop for it if you want, but I would not recommend it. I would not recommend it. Okay, so let's begin. I'll just briefly explain to you what this does, but you don't have to worry about it. I store the island in here, right? We've got a width, we've got a height, and then we've got the 2D array for the array, right, for the characters. Then we've got main, so we'll just kind of open up this file. We'll store its height and width. We'll allocate that array. Then we're going to print the island. And then we're going to count the number of square miles per island, all right? So we're actually just going to not look at this. All right, let's kind of put this away, and let's start with this. Our task is to write I want this to be capitalized, write a recursive function to print the island. Write a recursive function to print the island. So let's write the for loop to do this, right? Here's the for loop. You've seen this before. You're going to say, I don't know, for int I equals 0, I is less than. It looks like we'll have our island. Now, if we're going to do row by row, we're going to want to do the height first. I++. And then we're going to have another for loop, right? For int j equals 0. J is less than the island dot width. J++. Then we're going to say cout the island. I guess it will be island dot island. At j I. And then down here we'll print a cout endline. So Chef asks, what are the y and the x getting passed to the function? Well, that's partially because it needs to be recursive. That's partially because of the recursive implementation. You'll see. So this is our for loop for this function. I want us to write it recursively. So let's first identify the base case or the building block. What's the smallest version of this problem? Here's the bigger problem, right? Print a string of characters. That's the bigger problem. Print a string of character. Now, what's the smallest part of this problem that you can identify? Is there any kind of single operation that happens here? I'll even let you look at the for loop. This entire thing prints the whole string of characters. What's the smallest thing? Synthos is exactly right. To print one character. To print one character. All right, that's the building block. That's the building block. To print a single character. To print a single character. Now we're going to want to identify the base case, right? So the work we're going to do is just to print a single character. Somewhere in here we're going to print one character. Chef, back to your question, we're probably going to print this character. Now we want a base case. So let's suggest that we're going to call this function recursively over and over again, printing characters. In what case should we not print a character? Assume that all of the indexes are passed in, right? The indexes could be anything. They could be 0, 0. They could be 1, 5. They could be 66, 66. In what case do we not want to print a character? In what case do we not want to print a character? Suppose, I'll give you a hint here. What if the island is a 5 by 5? I guess there's a little bit of confusion there. Maybe I should call this print grid. I think you're right. I want to call this print grid instead. When I say this, I want to print the whole thing, water included. I would like to include the water with this. So let's print the grid instead of that. Here's what I would say. If the indexes are out of bounds, let's say if the indexes are in bounds, we will print a character. We're either going to print the period or we're going to print the X. But if the indexes are out of bounds, there's nothing that we should print. Do you see how that could be a base case? So maybe we have a few base cases. Well, we'll see. Actually, we'll have a few cases, but there's only truly one base case. There's only one true base case, and that true base case is this. If the X is less than 0, and our Y is less than 0, or we'll have to develop this. You're going to help me with this, okay? Or our X is greater than and equal to the width, and the Y is greater than or equal to the height. We may edit that, okay? You're going to help me out, but we may edit that. So let's try to put a base case in here somewhere. I might just copy this, and we'll see if we have to change it. Do we have to change it? I'm not sure yet, but we'll add a base case here. All right, and in this case, we may just return. Return. My guess is that we will have to change it. But we'll start with this. At least we've identified some sort of base case. In some sense, it's out of bounds. So do you agree that if we're in bounds, we can print a character? Would you say that? If we're in bounds, we could probably print a character. Now, before we do that, can we identify any sort of reduction operation? This is a bit of a hard problem, all right? We're kind of jumping into it, so let's talk about a reduction operation here. In terms of this, some sort of out of bounds, what kind of reduction operation do we do? Any ideas? I'll take any ideas. What kind of reduction operation? What will take us to the base case? If we're starting at x equals 0 or y equals 0, what's going to take us to getting out of bounds? Do we want to do a minus minus here, or do we want to do a plus plus? It's a little confusing, isn't it? Because if we're adding to it, are we actually reducing? No, but we're thinking of in terms of the base case. Reduce to the base case. If you think about how we're printing this, we're going to start from 0, 0. 1, 2, 3, 4, 5, 6, 7, 8. We're going to start from 0, 0. That doesn't look right. Maybe it is. Nope. We're going to start from 0, 0. And we're going to work towards going out of bounds. So can you agree that it would be a plus plus, right? Yeah, so Chef, you're right. But notice if we're going to print this, we're always going to start here. That's kind of how the IO stream works, right? We have to print this one first. There's no other option. So we're going to start from 0, 0. In the reduction operation, we're going to be adding to x and to y. All right. So our reduction operation is going to be something like x plus plus or y plus plus. All right. So now we can try to do our work, right? Let's try to print a character. And do a recursive call. All right, so we're going to leave this. Like I said, we're going to probably change this. We'll come back to it. But if we know that we're not out of bounds, I think we can safely print a character. This is going to be the island, .island, at the x and at the y. Let me confirm that I allocated the... All right, we're going to swap it then. I did the height first, so we're going to do yx. Synthos asked the plus plus because the base case is the bounds of the island. Yeah, or out of bounds. The moment we go out of bounds, we're done. So if we're starting at 0, 0, how are we going to work our way out of bounds? We're going to take steps upwards. We're going to go plus, 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 plus. If we go backwards, then we're never going to print anything. All right, we're never going to print anything. So say we print our island, right? So this will print the character. Now let's consider some things. Let's consider some things. Say we just printed this one. All right, I'm highlighting this. Let's say we just printed that one. What's the next thing we have to print? In terms of coordinates, let's say we just printed, I want you, let me give it to you just so we're not confused. We're all on the same page. We're doing yx here. We're doing height first. So I just printed 0, 1. What's the next one I have to print? Plus plus on the x, right? Plus plus on the x. We're going to go plus plus on the x. All right. So we're going to want to print the next one. So what if we do a recursive call, print grid of our island from y, the same y, but x plus plus, or plus plus x. Or if you want to read it more English-wise, x plus 1. That moves to the right. Chef is getting, you're starting to see it now. You say once you hit the end of the row, y plus plus. So we're actually going to have to add a few base cases here. We're going to add a case in here. We're going to add the case in which x is greater than the width, but the height is less than, or the y is less than the height. We're going to add a case there. And y increments and the same thing happens. So If x is less than 0 and y is less than 0, yep. I'm actually going to say, I'm going to change this. If we've gone past the height, we're done. All right? If any of these are less than 0, or if the y has officially gone past the height, we're done. Because we want to keep in mind that maybe x will, whenever x kind of goes past, we're going to want to move to the next row. So we're going to say this. If x is greater than or equal to the width, what is the first thing I think we should do is maybe print an end line, right? Because we're done with the row. All right. Now we're going to do a recursive call. Now you guys gave me one of them, right? You gave me the y. What is the x? What is the x? Do we pass the width, or do we pass whatever x was, or what do we do? Zero, right? 0. I think that's our recursive function. Chef says, for the first if statement, why wouldn't you have the and instead of or, since we want both of those conditions to be satisfied? Well, here, I guess that's fine. I think you're correct. If either x or y is less than 0, then, yeah, we'll return. Or if our y is greater than or equal to the height. How's that? That's better, right? If x is less than 0, or y is less than 0, or y is greater than the height, we will return. So that's our base case. And then we're going to do some recursive work here. At first, you're like, what's going on here? So look at this. If x is greater than the island width, then we will, we know that we've reached the end of the row, so we'll go ahead and print an end line, and then we will recursively call on a y plus 1 and reset back at 0. Else, we know that the y is inbounds and the x is inbounds, so we will print the x, and then we'll recursively call on the x and move to the right. That's it. So it looks like our reduction operation is an x plus plus or a y plus plus, or even an x equals 0, right? If we're going out of bounds, let's fix that. Our base case will be this. Okay. And our recursive calls are here. So should we try it? This is not going to work, but let's try the other stuff. Let's try the other stuff. Are we having fun yet? I think we're having fun. All right, so it's going to want me to provide some islands here. It's going to want me to provide some. So let's just try a few. Let's try island 1.txt. Wow, that went terrible. Woo! Wow. That's awesome. All right, let's go look at that island. That looks probably like an issue there, doesn't it? Whoops. Let's fix that. Let's fix that. That's better. That looks like our island there, doesn't it? And then this doesn't matter yet, all right? This doesn't matter quite yet. Let's try our next island. Island 2.txt. It looks like I messed that one up too. Why did I edit these? I'll just have to go through and fix them all. How about we don't do island 3? All right, that looks better. Did I save it? That's the question now. It's been saved. Let's try that one more time. That's better. There's our island, right? We can try again. Island3.txt. That looks good. Then we'll try again. Island4.txt. And it looks like we got it. Cool. So we actually don't have much time left. So here's what we're going to do. Listen up here. You are going to have to practice your recursive functions. So here's how your homework's going to be for this one. Now, we're not going to worry about it yet because we've got an assignment right now and we've got a test next Tuesday. But after that test, I'm going to assign you some recursive homework. Now, the recursive homework is you're going to solve kind of different programs. They're going to be kind of smaller problems. It's not going to be like write a whole program to do this thing. It's going to be like write a recursive function to solve this problem. So the first two will be pretty easy. All right, those will, I mean, at least in terms of recursion. All right, so you're going to solve kind of two programs. I'll make you count the number of characters in a string. I'll also make you write a program to tell me if a string is a palindrome. That is race car. Race car is a palindrome because it's the same forward as it is backwards. Okay? So your first two problems will be easy ones. All right? Writing recursive functions to solve those problems. I think the third program will be to solve this one. What does this one look like? I want you to count the number of square miles per island. That is, in this case, we'll start with a simpler one. I want you to count the number of square miles of this island. So there's 1 square mile here. That's an X. There's 1 square mile. There's 2 square miles. There's 4 square miles. So there's 4 total X's, meaning 4 square miles. I want you to count the number of square miles per island. So let's say we move to island 4 here. You'll see that these islands are different. This one has 5 square miles on it, and this one has, looks like 9 square miles on it. So that will be your third problem, and then the fourth problem will be a hard one. But you will be practicing your recursion, okay? So we'll go ahead and let's save that for the homework later. On the review, I'll make you practice some basic recursive functions that you might see on the test. None of your functions on the test will be like this one, but they will be more like the power that we did today. All right, if I ask you any recursive question on the test, it'll be something like this. It won't be print a grid. All right, so I'll include some kind of recursive questions to practice on the review. I'll also include a review program question, and our homework for this will be pushed until Wednesday. Don't be terrified. So that's all I have for you today. All right. When it comes to recursion, you just have to practice. So I'm going to put some practice questions on the review. I want you to practice them. Please come to me if you need. But the more you do this, the easier it will be. The thing is, you have to think recursively. You can't just go, I know what to do. You have to sit there and go, what might my base case be? How can I break this problem down? Okay? So, I hope you guys learned something today. I mean, maybe not so much learn, but you saw some of this stuff in action. Okay? You saw some of this stuff in action. So, that's all I have for you. You're welcome to come to office hours if you'd like. If you guys want to, I don't know, Chef, do you want to hang out for a second? And anyone else who wants me to try to answer that question from earlier? Or we can meet in Discord, either one. Is there anyone who would like to hang out? Please let me know. If you don't want to hang out, you can go. So Top Wolf, yeah, have a great day. Cade, have a great day. CS202 student, you're welcome. You're welcome, Nicholas. I guess my question is, does anyone have class at 1 p.m. that would like to be here? Does anyone have class at 1 p.m. that would like to be here? You want to hang out? All right. So hang out if you'd like. Otherwise, you're free to go. Turbo, I'll see you later. Giovanni, absolutely, you're right. This is unary tree. At most, it calls itself once. It's either the if or the else. Very good. Yes. At most, it's unary. Very good. Okay, that's fine. Yeah, I'll do that. I'll do that. So just hang out here for 1 second, and we'll talk about that. Let me just get a... Just going to do a standard text file here. Okay, so if you're going to do a pushback function on your dynamic array, it's probably going to look something like this. Void pushback. And you're going to take some type parameter, right? Type T. Now recall up here, you've got a class dynamic array. Dynamic array. Right? And in your privates, you have this type pointer array. And you've got an int size. All right. Since you said the memory approach, we're not going to have the extra. So it looks something like that. Obviously, this is a template, right? I'll let you do that on your own. So, Synthos, don't go anywhere. This will be the same. Synthos, in your terms, you're just going to say if you want to, you can have the max size. And you're just going to say if the size equals the max size, then you'll have to allocate. Else, you just do the insert. All right? That's it. If you're doing the memory efficient approach, you just take away these if statements. So that's it. I wouldn't go anywhere. This is definitely helpful to you. So, at this point, we can suggest that we have some array of some size. It has some elements in it. Okay? Just has some elements in it. And now we have a type T coming in. Okay? We have a type T coming in. And we want to say, I want to put 7 in this array. So obviously the current size is 6, right? Size is 5 right now. Size is 5 right now. New size needs to be 6. Now, we can't just add memory to this, right? So Chef says, are you going to use the specialized CTOR or the copy CTOR? You could, if you wanted to. I mean, I'll show you how to do that, but let me finish this one. I mean, you could, but at some point here, you actually have to edit this thing. You have to edit this thing. So if you're gonna use a constructor here, you need to generate one of these parameters. Meaning you're gonna need to make this array. does this make sense? You're going to need to have this array here. So this was before. This is before, and the one that you want is here. This is after. This is the after array. This is the before array. If you want to call that, if you want to say something like this equals a dynamic array, like new array with size +1, you still have to make this thing, right? You have to make that. You can't like you can't just you can't wing it. You have to make this. All right, this is requirement. So you could try to use the constructor, but I would not recommend it. Right? I wouldn't use the constructor. Here's what I would do. Let's talk about what we would do. All right, what would we do? Well, we would probably say something like type new array equals, I don't know, perhaps a new size or a new type. And what's the size of this one? What's the size of this one? What do you think? All right, so this is kind of step one. Allocate new memory. All right, yeah. If you want to hang out, you're welcome to. But I do know I've got a few people here, right, that might be interested in this, so we might as well finish it out. But if you think you're good to go, you can go, right? It's going to be the old 1 + 1. Chef says array.size, but notice we're inside of the object here, right? So if you want to say this size +1, that's fine. Or if you just want to say size +1, that's also fine. Okay. So now we have a bigger one. So I'll let you kind of do this, but step 2, you have to do a deep copy. All right, step 2, you have to do a deep copy. I'm not going to do this one completely for you, but you got to do some for blah, blah, blah here, right? And then in here, you got to say new array somewhere at I is equal to the old array at I. Somewhere in there, you got to do that. Because they're dereferencing here. And in some sense, you kind of have this blank array now, right? You did allocate something, and it's blank. 6, 6. Right? So you're going to have to go through this one and copy those in. You'll have to say this one's 3, this one's 4, this one's 5, this one's 6, this one's 8. Or 8, 6. I guess I messed that up. Right? And then at this point, you'll notice you have this empty spot, right? Yeah, you're welcome. You have that empty spot. So step 3, you got to put in the new element. All right, I think you can figure that one out. Step 4, I would say make an adjustment to your size at this point. Right? What's that? That's size +1. Make sure that it's recorded. And then step 5 would be to deallocate the old one and overwrite it with the new one. Overwrite the pointer with the new one. And what do I mean by that? Well, I mean, like, here you're going to say, hey, the array is equal to the new array. And then if you want to avoid the alias, you can say new array is equal to no pointer. So I think Chef's good. Nick, Giovanni, or Uchu, or anyone else that's hanging out. Does that make sense? Are there any questions about what we did here? We did a step 1, allocate, a step 2, a deep copy, right? Step 3, we want to put in that next element here. Step 4, we'll make an adjustment to the size. Step 5, we'll deallocate the old array and overwrite the new array. All right. All the other ones look a little bit similar to that, right? If it's push front, you're going to have an empty spot up front. So Synthos. So the old size is 5, right? The old size is 5, right? We're doing pushback here. So that's an index 0. That's at 1. That's at 2. That's at 3. That's at 4. Where do we put the new element, Synthos? The old size is 5, which means valid indexes are 0 through 4. Where does the new element go? Five. So what does that look like? New array size equals whatever we called it. Up here it's T. That's T. So Giovanni, I just be careful with that, because remember the old size is 5, and you can never index an array at its size. But if the array is 1 bigger, then you can index it at 5, and the new size becomes 6. So, Giovanni, the thing is here, where do we put it? We put it in the size index. The old size was 5. Now we've made the array 1 bigger, so where's the new index? It's at 5. Does that make sense? It's not the old size plus 1, because then you would be going out of bounds over here. That's number 6 right there. Synthos says, would it be the same for time efficient? Yes, to some degree. I'll put that skeleton just in front of you a little bit. It looks mostly the same as above. But here's what you may want to check first. All right, you might want to say here if our max size equals our current size. And what does this mean? Synthos, can you tell me specifically what does that mean? In English, when the max size is equal to the current size, what does that mean? If the max size is keeping track of how much space is in the array, and the current size is keeping track of the number of elements in the array, I imagine that this would mean that there's no more memory. But they're both integers. Synthos, they're both integers. That's saying that you have an array here that's x, 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 x. Yes, Uchu's right. There's no more memory. So the max size of this array equals 4, and the current size of this array also equals 4. When we're looking at this one, x, x, x blank, the max size of this array equals 4 still, but the current size is only 3. Because this is empty. This is an empty spot here. There's nothing there. So we can put something there if we want to. So if the max size is greater than the current size, you have some room. You have some room. All right, so Synthos says we need to allocate another. If you want to do max size, it's up to you. Here, I'll show you what I would do. But you have two cases. Here you'll say, kind of, if the array is full, right? You're going to need to allocate some stuff. But down here, let's say you've skipped this part, or you haven't. At some point here, you can just say array at the current size. That's going to equal to our new element, right? T. And then you can say the current size plus equals 1. in fact, this code will always work, right? Because you're just going to plop something in there. Just going to put something in there. So this code always works, right? There's an empty spot, you're going to put something in there. But here, if the max size equals the current size, you're going to do the same thing. Step 1, allocate a new array. So you might say type new array equals new type. And let's say, how about the max size plus 100 or something. You just get 100 more spots. And then here you can say the max size plus equals 100, right? So then you add to it. And then you got to do a step 2 deep copy, right? And then you can just copy everything else up above we did. Do a deep copy, delete the old array, and then overwrite the new array. Overwrite the pointer with the new array. And then this is kind of the step part here where you insert it. It's okay that this is out here. So is that helpful to you? Does it make sense? If we run out of memory, you're just going to allocate an array that's bigger. You're going to want to make sure the max size goes up. Then you're going to want to make a deep copy from the old array to the new array. Then you're going to delete the old one, and then you're going to want to overwrite the pointer with the new array. It's almost the same. It's almost the same thing here. In this case, you're just going to allocate 100 at a time. Up here, you're only going to allocate 1 at a time. So it's a slight difference, but mostly the same. So if you're good with that, I will call it here. Are you okay with that? You can come to office hours if you'd like. So, in fact, I will call it here, but feel free to message me if you like. I will be available. All right? So I'll see you guys next time. Thanks for hanging out, and thanks for asking questions.